let's look then at what the challenges are in designing radios for these applications. So there's pressure to reduce the radio size, weight, and power, or SWaP, to enable increased radio density. And I'll talk a little more about that in a minute, but that's one of the key pressures that a radio designer is facing in designing radios for these systems today. The proliferation of band variants and output powers. So it used to be that back in the good old days of GSM, there were just 4 bands. You had 800 megahertz, 900 megahertz, 1800 megahertz, and 1900 megahertz. Now, fast forward to today, you have over 40 LTE bands, and it grows every year. Not only that, but you have a slew of output powers and different bands counts and antenna counts. And so this makes life very complex for the radio designer, as the matrix of frequencies, output powers, form factors, and antenna counts keeps growing. So finding a common platform solution to address all of these is key to success. And then finally, you have time to market pressure. So in the comms industry today, it's literally becoming a race to the pole. When operators issue an RFQ, the first vendor to match that output power, frequency band, form factor often wins the business and gets to put their box up on that pole. Okay, so I talked a little bit about the size, weight, and power issues on the radio side in these systems, but digging into that and adding a little color. Small cell radios need to support multiple bands while minimizing the impact on the power consumption and size. So the first small cells were single band solutions, and that was fine as the industry was kind of in its nascent stage. But now operators are demanding 3 to 4 bands in each small cell box, while remaining within the small form factors and power consumption budgets. And so the reality here is that these boxes are mounted in an indoor scenario on a wall or on the ceiling, and they must blend into the background. And then equally outdoors, they might be placed on a street lamp or on a pole, and the size of them is not allowed to increase as the number of bands that's supported increases. And then on the massive MIMO side, these take the traditional macro base station antenna count from 2T2R or 4T4R up to 128T, 128R at the top side. So that's up to a 64x increase in the number of radios. And these massive MIMO boxes will typically be mounted on existing macro base station sites or on the side of buildings or on the top of buildings. And so they must remain within the current defined weight and size that's allowed for these base stations. It's allowed to increase a little bit, but not too much. So as a radio designer, how do you reduce the system size, weight, and power while increasing the number of radios significantly? It's a real challenge. One way of reducing the size, weight, and power is by minimizing the power consumption. So that has a knock-on impact on the size and weight, because these systems are passively cooled with metal. So by minimizing the amount of power that must be dissipated, you use less metal, and hence the box can be made smaller and to weigh less. So how do we go about achieving that then? Well, power amplifiers, or PAs, are the biggest power hogs in these systems. And both small cell and massive MIMO systems require high efficiency PAs in order to minimize power consumption. So to operate a PA efficiently, it must be driven close to its saturation point. The top diagram here shows PA input power versus output power. And ideally, one would get an increase in power from the PA as the signal goes from input to output and nothing else. However, as you drive a PA in its most efficient form, near saturation, it generates distortion components. And these can be seen in the bottom diagram. They manifest themselves as out-of-band distortion, as you can see in this diagram, and indeed in-band distortion happens also. So this out-of-band distortion is a problem in that operators must comply with spectral emissions masks, and they're only allowed to transmit within the channel that they have been allotted by the authorities. So how do you get around this distortion problem? Well, there's a technique called digital pre-distortion that's been used that enables the use of high efficiency power amplifiers, and that's been around for a number of years, probably since the introduction of 3G technology. So in the diagram here, digital pre-distortion, or DPD, works by observing the output of the power amplifier via the observation path, as indicated in the diagram, and then that's taken back down and compared to the known good input signal that's running through the signal chain in the first place. A model of the power amplifier is built up, and then the inverse model is applied to the input signal to pre-distort the signal going to the PA. So the resulting cascade of this inverse model and then the PA model linearizes the power amplifier. And as you can see on the right-hand side, we improve the ACLR, or the adjacent channel leakage ratio. So we push down the distortion in the adjacent bands, and then in band the EVM, or error vector magnitude, also increases. So as I mentioned, this technique has been around for some time, and it's been very successful. However, the existing DPD algorithms are typically implemented in an FPGA. They're inefficient and do not scale with the antenna count as the antenna count increases. So most were not designed specifically for massive MIMO and small cell applications and carry a big overhead in power consumption and size. And the reason for that is that as we've moved from macro base stations down to small cell and massive MIMO, the output power of each individual PA in these systems is much lower than in the macro case. So as you go to linearize that PA, the amount of power you consume in that DPD solution is a larger total proportion of the total power. So spending time on the power consumption of that block is a worthwhile exercise.